So once again, we're going to start with something that is low dimensional. We call ourselves lower dimensional, I suppose. Dimension 1, 2, and 3, and then we'll see what we can say about what's going on in n-dimensional spaces. So just to build intuition for things as much as possible, starting with, as we did last week, it is distances, how we measure distances here, and then see how, and we realized it wasn't too hard, ultimately, to learn how to measure distances in the n-dimensional space. Okay, so now we're going to start with, once again, R1, R2, R3 to begin with, and then somehow we'll see what to do in Rn. It's all metaphors ultimately, and the metaphors are for vectors. You've certainly seen vectors that look like this. Direction and magnitude. It's better to, if you have any inclinations for physics, and by physics I mean high school physics. So high school physics uses maybe not using a lot of vectors, but some of them. And then you either think of it as velocities, forces, but primarily forces, and how they combine them. Okay, so you pull in this direction and that direction, and together they produce something. So we'll be using that to begin with. But there is an even simpler idea of just to get started with vectors, and that is displacement. So then you have 2 points, say P and Q. Okay, so these are locations, and right away you can think of them as location in any space you like. So it could just as well be n-dimensional, but it doesn't have to be. So if you want to start somewhere, start with things happening on the plane. Okay, so these are 2 locations, and then from locations you have P, then Q. So the order of things matters, and then you move on from the locations to the displacement. That's all. Which is denoted as PQ. Remember this from high school, maybe? Plotting points to begin with. So once again, Euclidean geometry, you have points, and then if you were talking about maybe triangles, and then you would say PQ is the segment connecting P and Q. What may not have come up is that order matters. That the order matters. So PQ is not the same as QP. Okay, so that's the main difference from high school geometry, or when we talk about displacements. Okay, but it is a good starting point and to understand the algebraic operations. Okay, so displacements they're kind of predict to have could be subject to algebra. Remember that I think I made that point that you don't really want to do algebra with locations, because what is the meaning of location plus location? But you can speak of displacements. How in this manner? So I have P and Q, and then R. Okay, then one displacement from P to Q. So this is PQ. The other displacement from Q to R, and then there is a third displacement from P to R. Right? Once again, order matters. They're very simple, kind of abstract motion that you can certainly imagine without making yourself think about physics. So this is not physics, right? Just you jump from one location to the next location, and then you have 3 displacements. So there is no time or anything like that. There's maybe just the order of these displacements of jumps matters, but otherwise there is no time. So there's no speed, there are no forces, nothing like that. It's not physics. So jumping from one location to the next, and we have 3 displacements. What can you say about them? these three displacements? No, let me make a remark here that when we set the distances aside, and we will certainly need them, but right now we concentrate on the algebra. You can even think about that we are done for the time being with geometry, the one that does measurements, and we move to algebra, which does algebraic operations, and then we might put them together, but not necessarily. So distances will help us later. At this point, all I have is three locations, three displacements, and what is the relation between the three displacements, PQ, QR, and PR?
Yes, technically PQ.
What?
PQ plus QR equals PR.
That's right. Indeed, what is the net result of you moving from P to Q and then from Q to R? The net result is you move from P to R. That's displacement, and it also takes you to right there to addition of vectors. By the way, once again, we're not doing physics, so in physics you might see notation is different. Say, I don't know, like this. Arrows above the letter, or maybe boldface for the letters. Also, it's all hard to write, and also it is typically for physics, and we're not doing physics, fortunately. So the way I'm going to be doing it, I will try to use capitals. I will use capitals for everything that is or may be multidimensional. Okay, so numbers will be lowercase. So x, y, z. By the way, the distances are, say d, are also lowercase. It's just a number, but locations, p, q, r, might be in a multidimensional space. So I will use capitals for them, and the displacement between them also will be capitalized. Okay. So that's the initial idea about adding vectors. In fact, if you to make this clear, I forgot to do something here. This thing again, I cannot catch it. Here it is. What was I talking about? In fact, this is the relation between how you can add displacements, but we have like two objects of different nature here: locations and displacements. Also points. So location points versus vectors, understood through locations versus displacements. So they are two different objects of different nature. So points are like dots, locations, and there might be distances between points, but you don't do any algebra with them. On the other hand, vectors don't have really distances between them to speak of, but they can be do algebra with. They also can be interlinked. Here's another one. So they are not disconnected. You can think of say PQ is equal to Q minus P. So from Q, I'm getting from Q to P. What is the meaning of that? It is a displacement, and we just write it as PQ, and that is a vector from P to Q. Okay, so alternatively, I can write as Q is equal to P plus PQ. So it's like consecutive. We're moving forward on, and I'm writing the next location in terms of the previous location. So my previous location is P. I add the displacement PQ, and I end up at the new location, which is Q. Okay, so that's just worth mentioning, even though in linear algebra we're not going to pursue this. It is actually a very convenient way to get started with some vector calculus. But we're gonna stick with linear algebra, and that is that we are pretty much will be concentrating on vectors, and points will be kind of ignored for the most part. So what I mean by that is that we're going to be doing algebra with vectors, even though this looks quite nice, and we certainly want to use it, but really we're going to concentrate on vectors that originate at the origin, start at origin. Okay, so like this. They can have different lengths, but the starting point is the same. So that's the origin. So that's what the part of this setup that we're going to actually investigate. That is this. That's the linear algebra. Okay, so once again, vectors are all originate from the same point. So we can still do addition. Okay, so let me show you that the relation between the addition that we saw over there and this. So it is I can, if I want to add two vectors, what do? I just move one and put its end at the beginning of the second. So say this is A, and this, well, let's put the capital here maybe. What's wrong with this thing? Say A and B. So A plus B, what is the meaning of A plus B? And this is the idea. I take my vector A and move, or which one? Let me pick B. I'll take my B and move it, slide it towards the beginning or the ending of the second vector. So this is a, let's call it B prime. B prime is a copy of B. In what sense it's copy? It has the same exact directions, the same exact length, but it just originates at a location that other than the origin. So that's just a matter of construction. So you may have seen this before. And then the end result is the addition of vectors the same as you see over there. So something, let me say this is A. Okay, A. B is in green. Okay, and then let me, oh, here it is, like this. Okay, so I'm taking orange and add green to it. Okay, so it is easy when they're placed consecutively. That is simply two consecutive displacements. And what do you do? How do you get those two vectors at the top? You just look at the beginning of the first towards the ending of the second. Okay, that's your combined displacement, the net result of that displacement. This is slightly more complicated, but still works out. If I just make a copy of B, so I slide my vector B in this direction, like along A, like this, and move the origin that used to be at the origin of B used to be at O. It becomes at the end point of vector A. Okay, so and then I add just the way I done it before. I just go diagonally. So it's a parallelogram, right? What you're looking at, and this is A plus B. So the same plan as before. So this is yellow plus green gives me the red, and it's the same thing here, even though the we have to do an extra step. The idea here is fairly simple. Is that just if you think of vectors as displacements, just too many of them. So every 2 point will give you a displacement. And this way we are cutting the number of vectors that we care about and have to deal with significantly much fewer. Okay, so that is the way it works out. You certainly can try to explain this. It is then this kind of, that was easy at the top to explain with, and we have with displacements. Okay, now at the bottom, it's not technically displacement. If I'm looking at A and B as two vectors, then it's really not, with originating at the same point, you cannot speak of displacements anymore. So you can think of these as forces, probably. And the forces doesn't have to be necessarily something harsh here. You can just think about an object being with two springs attached to it. So one spring is here, well, spring or rubber band, okay, and it is pulling in this direction, and there is the other one attached here and pulling in the other direction. Okay, so that's A. No. Like this. Okay, so you know what the end result will be. It will be pulling in the direction kind of in between the two, but depending on how hard it is being pulled in these two directions. So that will be as if you have another spring in between. Okay, so that's how we understand adding vectors. Another way to see it, if you don't like forces, think velocities. So imagine that how I can interpret this. Imagine that this is not an object attached to springs, but rather it's a boat. It's a boat. Okay, and I'm trying to cross a river, and then the green represents the flow. Like this. So same magnitude throughout, like this, right? So this is the flow of the river. And then what does the orange represent? It represents in which direction and how hard I'm rowing. So I'm trying to move in that direction, but the end result, it's not going to work out. What happens? What? Well, you can't move simultaneously, right? So So practically speaking, what's going to happen? You're trying to row across the river, and you see the opposite end right there. You want to just go straight and be on the other side of the river, but because of the flow, what's going to happen? You end up you will be pulled downstream. And that's what the addition means here. So you will be pulled in this direction, and then you, instead of, this is your intended target is here, and you end up instead over here. So that's the physics interpretation of adding vectors. So it could be both of these are physics. But you can interpret as velocity. This was about velocities in the sense, or you can think about forces such as springs. You can think about displacements as well. But ultimately, as we go to high dimensions, it will be about simply numbers. And remember, what a vector is. It's just in dimension 2, just as a point. A vector has 2 coordinates or more, and they're simply added consecutively. But before we do the algebraic angle, there's a second operation on vectors, and that is it's called scalar multiplication. So scalar multiplication. So this is what was it? Vector addition. Here. That's how we add them. And now scalar multiplication. You can also certainly think of how you can interpret scalar multiplication. What is a scalar multiplication? You really scale your say force. You can scale it by 2. So once again, there is an object, there is a spring. And then either you mill like this. No, this is an object. There's a spring. You can think of this either as the spring pulls you twice as hard. So does it make the necessarily this? I'm not even sure what it means from the physics point of view. If you will make your springs twice as long, will it pull twice as hard?
No.
I don't think so.
It should be tighter. Like if it's actually shorter and the pullovers are tighter.
Yeah, that's true. What if it is hanging on a string like this? Wouldn't no, I'm not sure what I'm saying here. So if you take two springs and attach them consecutively, it will pull the same as hard.
Yeah.
Don't you think it will be harder to? Yeah, that's true. It's like a string is attached to another string or is attached to a wall. What is harder? So strings attached to a string, which is attached to a wall. Or you have a string directly attached to a wall. Which one is harder? What? Which one?
Hopefully not.
No, I think the latter one, which is attached directly to the wall, will be harder to pull because there is no more room to pull off the wall. So, okay, so that's the thing about metaphors. They break down sometimes. So that's why mathematics doesn't really about metaphors. So anyway, okay, so here's an example. Certainly, you can imagine that maybe the sun becomes twice as large, right? And it will pull the Earth twice as hard, right? Distance is the same; it will be pulling twice as hard. So once again, so double, so 2. So if this is my vector A, then this will be 2A. Okay, so same direction, the magnitude is doubled. That's all there is. Of course, there's a trickier multiplication. So what if we multiply by a negative number, and that reverses the direction, which one that definitely does not allow us to do any kind of physics in that manner, because well you can't really change the situation in such a way that suddenly you have the vector points in of the force points in the opposite direction. But that's roughly what this is. So the same magnitude, but it is points in the opposite direction of the original. Okay, so once again, you can certainly find an interpretation for it. Okay, so that is just a way to introduce these things, and certainly multiplication by. Let me just put it in words here. Stretch. Well, so say CA is A stretched by a factor of C. Well, that's it. If C is positive. Okay. However, if C is between 0 and 1, right, then the stretch turns into a shrink, right? So stretched by 1/2 means shrink by 2, right? So well, let me plot it somewhere. 1/2 A. Okay, so let's do coordinates. But first, before we do coordinates, let's realize that, as always with vectors, there are always points, and anything multidimensional, they could exist in one-dimensional case. So one-dimensional. Let's just verify that whatever we have tried to understand makes sense in dimension 1. Adding vectors that lie entirely within a line. Okay, so one and the other, for example. So this is, say, B and this is A. Once again, let's not forget that this is, over here we have our origin. Origin is that point where all vectors originate from. Okay, so what happens? When we add vectors, well, if it makes sense, once again, think about it either being strings. So this time we have two strings, but they're aligned with each other. So what's going to happen is they will be pulling, well, you add the strength of the pull, right? Even though they are pointing in the same direction, doesn't really make any difference. What is important here is, however, what happens to the numbers. These two vectors then will be represented by their coordinates. There's only one coordinate in the one-dimensional space, so what happens to the coordinates? So if this is 2, say this is 2, and this is 4 over here, then A plus B will be, this is A plus B, and it's will be represented by what? What?
6.
Yeah, 6. Okay, so that's the idea of what happens to vectors. What happens to the coordinates or components of vectors as we add them, and well, we just add them one coordinate at a time. What's to be kept in mind, and that's why we still need to think vector even in one-dimensional case. It is when this all works out, even if the vectors are maybe pointing in the opposite directions. Okay, you still, what do? You still add. You don't think about what if are they opposite or different. You don't have to worry about it. You just subtract. So, for example, if I have a C over here, say -1 over here, then what is the A plus C? A plus C is simply, well, you don't have to think about it. Just add them together. So it's 2 plus -1, so it will be equal to 1. Okay. And as you can see, the algebra, the geometry works out too. Do you see the? So this is what's the geometry for A and C? Remember how we had vectors? This is A. This is C. What's the plan? How do we add vectors? Remember, you move, put the C at the end of A. Okay, so I put it C at the end of A here. So this is like C prime, a copy of C. And then the last step is to connect still the origin over here to the end point of that vector. So this is A plus C over here. Even in one dimension, it works out.
So this is vector addition and subtraction, right?
Addition.
One-dimensional, right?
One-dimensional vector addition, yes.
So is there one-dimensional vector multiplication, or is that what you're
Scalar multiplication, you mean. We haven't talked about anything else, but scalar multiplication certainly, say, if I want to have, well, how about 3C? 3C. What do? I could do this. One of the ways to do it is just, if the scalar is an integer, I can just repeat that vectors 3 times. So this is C, C, and C, and so what the end result is, the end result will be negative 3. Okay, or you simply multiply -1 times 3, and it is -3. So it's very easy with coordinates. Geometry, however, is just geometry just helps us to understand what's going on, and so that we wouldn't purely stuck with coordinates only. So that's why one-dimensional works out. What about n-dimensional? And look at it. With this addition, that picture that I created will probably just as well repeat it. So the addition of a second. The addition of vectors is two-dimensional. So it could be one-dimensional if we go down, but we can go up. What happens? Nothing. It's really the things do not become more complicated if we stick with geometry. So that's the advantage of geometry, that you can just continue on. And this is the picture we're looking at. I'm making up the picture. You can think of it as if it is on the plane naturally. I copy B, put it in the end of A like this. Okay, then connect these two together into my A plus B right here. Okay, but now, it's all, I was thinking as if it's all in the plane, but really is it? Does it have to be? No. So, plane. The answer is maybe. We certainly know that it's not one-dimensional. Okay, that we can see it's not one-dimensional, but it could be two-dimensional, three-dimensional, because that plane, these two vectors will determine one single plane. So even though each vector lies in the n-dimensional space, it has only 2 points to connect. It determines nothing but a line. So that's a line, and that's a line. So you have well, what do you have? You pretty much have nothing but a triangle. You have 3 points and lines connecting them. It doesn't matter in what dimension these points lie. The whole thing is two-dimensional. You can always fit a plane in a triangle in a two-dimensional space. That's just the thing about it, right? So we talked about that a little bit. So as long as the 3 points do not lie on the same line, the end result is a plane. You don't need more dimensions for that. So that's why the geometry is vectors, vector addition is so visual, because it is still two-dimensional. Same with with scalar. What is the dimension of scalar multiplication? So vector addition is two-dimensional. Okay, so you start with 2 vectors. If you have more than 2 vectors, you keep adding them. So the third vector, you can have one vector like this, and they are still in the plane, but the third vector might be pointing up, and that will take you to the third dimension, and so on. The more vectors you have at the same time, the higher the dimension is. But you can do it one at a time, just the way we did it last time. If you do it one at a time, you add them together, you have one vector, and then you take the next one, it's still two-dimensional thing. So let me make a little picture like this. So if I have 3 vectors, this is not two-dimensional anymore. But if I do it one at a time, so I do this just the way I did, right? Two-dimensional. This is two-dimensional. Adding first to the second is two-dimensional, and then I take the sum and add to the third. Once again, 2 vectors, and the whole thing is only two-dimensional. So, and the third one will be this. And so I have, what is it, A plus B plus C. That's what I'm talking about. So the purple ones is A, B, and C, and the orange one is A plus B, and the red one is A plus B plus C. And so even though the whole thing is three-dimensional, the addition itself, carried out step by step, is two-dimensional. Okay? So geometry works. It certainly helps us to understand, to imagine what's going on in higher dimensions. What about scalar multiplication? What do you think its dimension is? What?
Extending, stretching,
yeah.
And the lengths.
Yeah.
Just like one-dimensional, right?
It's one-dimensional, that's right. It's one-dimensional. It's if you have a vector and then you stretch it, and you stay within that line. You're not going anywhere. You're not turning or anything. So it's one-dimensional. So it's very convenient to have all the algebra taken care of in low dimensions. Okay, so let's turn to a little bit of algebra. It's not. Things start to become more complicated, as a matter of fact, already. So let me summarize what I have here. So okay, so there are entities that we're dealing with are, I'm ignoring points, but we still have vectors, and the second one is still numbers. So that's the key where a difference from what you see in algebra elsewhere. It was algebra of numbers, and then you think, well, let's start with vectors, and we'll just have an algebra of vectors. That doesn't work. It's not algebra of vectors. It's algebra of vectors and numbers. So you're adding vectors, yes, but then you do scalar multiplication, and so you multiply vectors by numbers. So this is scalar multiplication. The scalar, what's the meaning of scalar? It's a number. Okay, so then if you multiply 3a, that's the interaction between vectors and numbers. So even in one-dimensional case, we have to be careful to understand if we're treating this particular number as a vector or as a number. Well, certainly in high dimension there is no confusion, so we know that this is a vector, and we might stretch them. Okay, so and then the magnitude of what can happen really explodes, and some simple algebraic things become less obvious. Let's examine. Well, let's start with a purely vector algebra. So pure algebra of vectors only, and that's what is it? It's just addition. Algebra of vectors only. So, by the way, there is an algebra of numbers only. Right? That is the algebra that you know. So this is familiar. And now what new things that we're going to be considering is algebra of vectors only, as well as algebra of vectors and numbers. Okay, so this is all okay. We know how to do this. And we'll be invoking some ideas from there. And let's just look at vectors only. So a plus b is equal to b plus a. How about that? Remember what's called? I mean, it looks like it could be, these could be numbers. So that's the thing about algebra of vectors. Everything looks like you're dealing with numbers, even though they are not. So you have to be careful sometimes what you are allowed or not allowed to do. But so far so good. This is. Let me demonstrate you what I mean here. So I start with a followed by b. Well, no, let's not follow. The idea is that they're side by side, so this is A and this is B. Okay, so I can carry out left-hand side, right-hand side. They are opposite, right? So one is I first take A and then add B. So how? I take my B and attach it to the end, right? So this is A plus B. This is A plus B. So once again, two-step procedure. From B is copied, attached to the end of A, and then you connect the origin to the end of that vector. Okay, so that's my A plus B. On the other hand, the other possibility is that do the other way. B plus A, that's the right-hand side. So this is one, and then there is the other. So once again, this is still A, still B, so the same exact vectors, but now I take A and attach it to the end of my vector here. So this is my A prime. Okay, and then I connect my origin to the end of this vector. So this is B plus A. So once again, to repeat, this is B, this is A, and I can do this, and I can do that. Okay, so looking at the picture, what can you say? So So any comments?
What are you asking? Right.
So
True.
true. Okay, yeah. So true. This one is true. Okay, so I wrote the equation that looks like we know it should be true for numbers. Now we can justify that it's also true for vectors, and this geometry explains why. So the picture seems to be convincing, but can you say anything why to comment on the picture so that to confirm that it is indeed the same thing? It's not entirely doesn't entirely look the same, right? So what are we talking about? There are two pictures, and they're supposed to present the same thing. The green one and the red one are supposed to be the same thing. So why is it the same thing?
Like whichever order you do it, you're traveling the same distance in the same direction. So you're heading the same spot.
Well, there seems to be two pictures. They're really not related to each other just yet. The first and the second. So how do you know that the endpoint of green one and the red one has the same endpoint? I mean, if we already knew that, then we wouldn't have to worry about that. But geometry should explain why it is the same point. No, but, so it's I'm trying to maybe remember some things from high school geometry. Well, I mean, actually, it's not entirely obvious, I suppose. But what I'm talking about is a parallelogram. Parallelogram. What is a parallelogram? It is opposite sides are parallel. Okay, so then if I start with two sides, then I know where the other two sides are supposed to lie. So if I start with this one, right? So I will, and I have the endpoint. I can draw the other one like this. Okay, so that creates two parallel lines indeed, and I do the same with the other one. So I start here, and then I shift it parallel like this. Okay, so far so good, right? So there is no doubt about what's happening here. It is, and once you have that, so parallel lines, and then two more parallel lines. Okay, and what we're saying here, however, is that doing it the way I did, once again, two parallel lines and two parallel lines, the opposite sides will be equal. That's what about the parallelogram. So parallelogram, by definition, is simply quadrilateral with opposite side parallel. That's it. So that's the definition. That's what we have. But the reality also, that's a theorem, as a matter of fact, that says that the opposite sides not only parallel, they're equal in length. Okay? So once again, opposite sides are parallel. And then we conclude that they are also equal. If they are equal, then the construction that we have on the left confirms our conclusion. So then the picture not only depicts a parallelogram, it also illustrates vectors as well as their copies. So if this is A, this indeed we have demonstrated the opposite one, well, it was a B, will be on the opposite side. Not only parallel, but also of the same length. So B prime will be here. And similarly, A prime here. Okay, so once you have that, you have parallelogram, you have opposite sides parallel and equal in length, then indeed A prime is a copy of A, B prime is a copy of B, and then you just connect. What's left is just you have a diagonal, right? You have a diagonal. That diagonal represents the sum of A plus B, B plus A. So the word for this is, I hope you remember, what's the word for it? What? Commutative property, yes. Okay, so, there is not entirely the end of it. Do you remember any other properties of algebra of addition? Algebra of addition. What do you? Commutativity. What else? What? Associativity. Okay, give it to me. Associativity.
A plus B in parentheses plus C equals
That's right.
A plus B plus C, for instance.
Okay, so let's illustrate that. It's slightly more complicated because you have three vectors, so the whole picture might hypothetically be three-dimensional, but no higher than that. Well, but fortunately it's not. It's also possible to do so. So three vectors, A, B, C. Okay, so let's illustrate, not going too far into this, but let's just illustrate to convince ourselves that it's true. So we know it's true for numbers, and now we do it true for vectors. So well, let me start over. Okay, so A, B, C. Okay, so A plus B. Okay, let me try. Okay, so A, I'm doing the left-hand side. So A plus B, I'm adding C. I'm adding B, like this. Okay, so that's my B, and then I'm supposed to, after that, I'm supposed to add C, this one. Okay, so that's the left-hand side, A, B, C. And AB, where let me mark this again. So this is A, this is B, this is C. A plus B is this. Yep. A plus B is here, and then you can also see the A plus B plus C, this one. A plus B, the red one, plus C. Okay, now do the opposite, the right-hand side. So I will be doing first B plus C, and then the convenient thing is that I could add later, because we have commutativity already. Right, so I will go with B plus C, B like this, and C like that. Okay, so then this is my B plus C. Okay, and then I have to add A somewhere. Okay, I could add it after or before. That doesn't make a big difference. I'll probably stick with it like this, with the same order, A here. So A plus B is, A plus B plus C. Okay, so B plus C is the purple one, and I'm just adding the last one. Okay, so I have one more color here. Yeah. Like this. So this is supposed to be A plus B plus C. Okay, makes sense? Okay, so once again, let's appreciate that it's not the same thing, right? So I did A plus B, created A plus B, red one, and then to that one I added C, and that's how I get the black one. Okay, so for the second one, I first did B plus C. That gave me the purple one, B plus C, as you can see, and then I added A to A. Okay, so do you see that's the same thing?
Yes.
Really?
Why? Same way.
I think it's, I'm convinced. It looks the same. Okay, so we'll finish next time.